Hi, welcome back. In this Earth Science lesson, we will be discussing the alternative energy sources, the most popular ones, at least. Last time we covered fossil fuels and pretty much how fossil fuels are used for, well, all of our energy needs. And that takes care of transportation and electricity and manufacturing. Now with alternative energy, we are really only focusing on making electricity because, as you'll see pretty quickly, that's really the only application where alternative energy can take care of it. Theoretically, if all cars were electric and our energy grid became totally nuclear and hydro and solar and wind, then transportation would be taken care of with that as well. At least like consumer transportation. I can't imagine that electric planes will ever be a thing, honestly. I hope I'm wrong, but so as we go through this, just be thinking of electricity for the most part. Now, as we said last time, again with fossil fuels, the big advantages they have are the fact that they are pretty cheap because they are extremely abundant and because they're very energy dense. And fossil fuels are easy to move around and they make energy whenever we need them to. So they're very reliable. Now again, with energy, we either try to make mechanical power or make electricity. So we, as I already said, are focusing really on electricity production. Here's the coal burning plant. So just to understand, where does electricity come from? Well, we burn a fuel to create steam. That steam has a lot of kinetic energy. That steam pushes turbines, which rapidly spin a generator. Now, if you don't know anything about electric motors, they can only produce electricity if there is motion. You have to have a strong magnet and a coil of wires, and as either the magnet or the wires rotate, it creates an electric current. That's what coal burning power plants, oil burning power plants, and coal burning power plants do ultimately. They boil water to make steam to spin these massive electric generators. And that's kind of what we'll see with almost all of these alternative forms of energy as well. So we'll begin with the sun, solar energy, which harnesses the energy from the sun. Now the big advantages to this is you have to make the materials, but the materials have no emissions. There's absolutely no input or output to a solar panel. They have absolutely no moving parts, and so they don't require maintenance either. But the major drawback, obviously, is that solar panels make electricity only when the sun is out. And most people are at work or school during the best hours to get energy for their home, which is the most practical application for solar energy for the most part. Now, there are ways to sort of capture that electricity that are starting to be developed. Here's just sort of a graph of where you can get your money back or in how much time with solar panels. That's kind of another disadvantage. If you live in a temperate, high latitude area, solar panels are kind of worthless for most of the year because the sun doesn't rise very high in the sky. But in a lot of places, they are pretty useful. Tesla, they make batteries for cars. They also will make batteries for your home. So you can capture all of that solar power while you're at work, and then at home, your house is operating on free stored up electricity that you got from that your solar panels collected throughout the day, which is an advantage and it helps pay it off. If it's not gonna help people save money, if it's not cheaper than the alternative, then we're just not gonna do it, right? There's actually several different ways to do solar power. The most common one we know of are the solar panels. So those contain what are called photovoltaic cells. And I don't really understand exactly how they work, but they're bombarded with photons and a pretty weak trickle of electricity comes from that. But solar panels have gotten exponentially more powerful and cheaper over the decades. Then there are solar mirrors as well, which reflect heat from the sun to boil water to make steam to power the electric generator, like the power plant does. And some homes have solar collectors, which are literally just black boxes on their roof, And that gets really hot, and then that heat can be used to heat water, so you're not burning natural gas to do it or whatever. It's free heat for your home, essentially. And also, a well-built house can be energy efficient and take advantage of sunlight. So here's a diagram of a solar panel. I'm not going to expect you to know how they work. I don't know how they work, and I can't teach it to you, therefore. But it's okay. We just need to know what these forms of energy are. Here's an enormous solar collector array. So these mirrors are articulated. They track the sun and bounce that light to the tower. And again, boils water, makes steam, generating electricity. Here's sort of a diagram of these solar collectors. So again, the heat is just captured and transferred around for various tasks. And as I was saying, I used to live in a very cold place, Watertown, South Dakota. And in the wintertime, my house had windows towards the south, and there were really giant windows. So in the wintertime, certain days in the winter, even though it was very cold outside, the sun would beam in warmth through the windows, and it would naturally heat up the house. So there's less need for burning natural gas or electric heaters, which get their energy from a coal-burning plant, perhaps, to heat your home. So that's where I was talking about an intelligently built house. In terms of energy production worldwide, Germany produces the greatest total amount of solar electricity by kilowatt hours. And then next is Italy, of all places. Now, notice how Germany is 7.5, Italy's 7.7. That number is the total percentage of their electricity they get from that source. But the number of kilowatt hours, Germany's making the most of them. United States, we're a huge country. We only get 2% of our total electricity from solar, but the number of kilowatt hours that represents is greater than Japan, who gets almost 6% of theirs. The country that generates the most electricity as a percentage from solar is Honduras, but the total amount of electricity they make, it's a small country, small population, not super urbanized, industrialized. So the total amount of electricity they make is fairly low. For example, China's capacity to make electricity through solar is 43,530 megawatts, whereas Honduras is only 391. So there we go. Moving on to wind. So there are new different designs for wind turbines. I've seen sort of vertical ones that vibrate back and forth, but for the most part, it's really just captured by wind turbines. And a wind turbine is really, they're enormous, but they're very simple. They simply, the blades capture wind and spin, and then there's a generator inside of there. So we're not having to make any steam or anything like that, but we still get this rotational energy, and it creates electricity. And wind has by far been the fastest growing alternative energy for the last probably closer to 20 years now, and it probably still will be in the future, although solar is becoming really, really, really big. So there's sort of, the inside of a wind turbine, what it kind of looks like. Basically, just understand there's a generator inside of there, capturing that rotational energy. Wind is the green portion here, so in 2000, there was almost none of it, tiny little sliver, and now today it's very, very, very large. This is just our capacity, so it's been growing. I don't know what the heck happened in 2013, but we really didn't install very many new wind turbines. Texas makes the most wind energy in the United States, followed by Iowa, Oklahoma, California. I used to live in South Dakota, that's why I put it there. And when I put this together, this is like probably 3 years ago, Connecticut and North Carolina made absolutely no electricity through wind. I don't know if that's still true or not. Maybe it is. Who knows? So the drawbacks with wind power. Again, it's not always windy. So there's your one problem. So it's not like it's universally applicable to everywhere. Some places just don't get a lot of wind. Here where I live in California, there's almost never any wind, which is really nice, kind of. Back in South Dakota, it's so windy all the time. I hated it. But we had large capacity for wind turbines. But the amount of land and raw materials that is required to make electricity through wind turbines is gigantic. You can just read the numbers right here. A coal plant or a natural gas plant has a much smaller, not carbon footprint, but a much smaller footprint in terms of raw materials. But, a coal-burning power plant burns millions of tons of coal throughout the decades that it's running. A wind turbine burns none at all. The fuel it uses is free and has no emissions. You just got to make the stuff in the first place. Okay, moving on to hydroelectric. So this is where we use falling water. Again, no steam is being produced. So what a dam does is a dam is a potential energy generator. It lifts up the water to an extreme degree, and then that water falls through the dam and strikes blades, a turbine again, to rotate it. And hydroelectric forever has been our dominant alternative energy source, but it's really been static for the last about 50 years or so. So this is not the Hoover Dam, it's some dam somewhere in America, I'm not sure which one. But we, again, create tons of potential energy, and then that water flows through the dam and rotates these turbines, making the electricity. This is the inside of the Hoover Dam. It's just remarkable to me that this thing was built in the 30s. The largest dam in the world, the Three Gorges Dam, it's 1.25 miles across. Compared to the Hoover Dam, is only 0.22 miles across. Sorry for using bald eagle units. But it's really a monster of an invention. Now there's other types of hydroelectric power, tidal power, which has an extremely limited capacity. But basically you can construct a dam in a bay, and the water flows out of the bay slower than it fills it in. So you can get, for a few hours a day, a dam in a sense. It sort of comes and goes. It's not always running, but it is there. Tidal power can also be used basically with underwater wind turbines to an extent. So as tides come in, there actually is a flow of water in that direction, and these can be programmed to make electricity all the time as those tides come in and out. But it's very limited, and it does not have a capacity to make very much electricity. The advantages to hydroelectric is that we can always make electricity from it, day or night. The water is reliable, and the fuel is completely free, so there's no cost whatsoever towards that. The disadvantage is that we've kind of hit our capacity. In the United States, we almost certainly have. Worldwide, we could theoretically perhaps double our output for hydroelectric power, but that's really it. The world's population is only going to increase, and still today, half the world's population consumes hardly any electricity whatsoever. So hydroelectric cannot be the future. It can be a major contributor, and we should use it, but it really can't solve the problem. And I think I said everything there. So moving on. Other disadvantages are environmental. So building dams floods huge portions of a river, and so that disrupts ecosystems upstream, but also downstream. The amount of water that flows out of a dam is severely reduced. As a matter of fact, the Colorado River most years never actually reaches the ocean, which is really bizarre to think of. Here's the Hoover Dam with the Colorado River right next to Las Vegas, but here's the Colorado River in Mexico. The water should flow all the way to the Gulf of California, but it doesn't. It just simply dries up. Now, here, the results have not been really all that dramatic, but in China, there's a species of river dolphin, actually, which they're not extinct yet, but the population numbers are so low, it's almost certainly going to go extinct in just a few years. And there are many, many other, I don't want to get into all of them, but there are many other environmental issues that come up with this, and political issues as well. You're talking, when the flow of water is reduced, well, say one country builds a bunch of dams, and that water flows to a different country, but the water doesn't flow there anymore. And maybe those people are fairly poor and they do a huge amount of agriculture that depends directly on having access to water, they don't have it anymore. That would kill people, huge numbers of people. So there are political things to think about with this as well. Moving on. Geothermal, fairly simple. Normally we have to burn things to get our steam, but there are natural pockets of steam that exist in the ground. So countries that have a lot of volcanoes have a lot of geothermal energy as well. The drawback to this is it's actually, unlike most of these others, it's a non-renewable resource. That steam will not last forever. The only other alternative energy that's non-renewable is nuclear energy. But geothermal, it's going to be temporary. I really don't think in 500 years will we still be using it. I kind of doubt it. Maybe in a few special places such as Iceland, but really no. And as you can see here, Texas makes more energy from wind than the whole planet makes from geothermal. But if it makes sense to do it in one place, by all means, we absolutely should. And there's geothermal, or it's actually over here, pretty small share. Here's a geothermal plant. Here's sort of a very, very simple diagram. Now you can prolong it by pumping water back underground to get more steam, but it is technically non-renewable. And we're the world leader in geothermal. As far as a percentage of how much of our electricity is geothermal, I don't know. I seriously doubt that it's more than 1%, but there you have it. Notice, so I was talking about earlier, all of these countries have a pretty decent number of volcanoes. The United States actually has a few of them. The Philippines is an archipelago, a volcanic island chain. So is Indonesia. Mexico has quite a few number of volcanoes as well. New Zealand, again, it's a string of... New Zealand's really just 2 islands, but they are volcanic in origin. Italy, there's Vesuvius, obviously. Iceland literally is a volcano. A few volcanoes, I guess. Kenya, Mount Kilimanjaro comes to mind. Japan, Mount Fujiyama comes to mind. I don't know any volcanoes in Turkey, but there you go. Now, nuclear. Nuclear is great because the fuel source is the most energy dense by a long ways. And the nuclear power plant is structured very similar to the coal plant and has the same advantages as well. So, radioactive isotopes, we don't burn them, but they naturally get very hot. And that heat is used to boil water to make steam. So, again, the diagram of the nuclear power plant is very, very similar to the coal plant. Now, it's trickier. It's theoretically more dangerous, although not really, because fewer people have died in nuclear accidents than in the whole history of our planet than typically die every year in coal and natural gas industries. Nuclear is really, it's actually safer than solar power, because people die from falling off of roofs installing it. Statistically speaking, nuclear is basically the safest type of energy. It's just that it has the potential to go pretty wrong. Here's the inside of a nuclear reactor. I don't know how they got this picture, but whatever. And here's just an animation, a GIF of what the heck goes on. It's a chain reaction. So you bombard an atom's nucleus with a neutron, and that causes it to split. This is known as fission. And that releases 3 more neutrons, which then go on to bombard other nuclei. And the amount of energy released is proportional to the speed of light squared. We're making energy, E equals mc squared. Mass times the speed of light squared. There you go, Albert Einstein. Squeezed him in. Actually, it's pretty surprising. In the United States, we get almost 20% of our electricity from nuclear. We could go so much farther with nuclear. France gets 75% of their electricity from nuclear power. They've really done a great thing by leading the way in that. And if you ask me, in 100 years, how will the energy sector be transformed? I think that virtually all pedestrian cars, like commercial vehicles, will be electric. But I hope that we basically invert, whereas today we get 80% of our energy relies on fossil fuels, I would hope, and it seems like the most practical answer or solution, is that 80% of our electricity will be nuclear derived, because it's really the only one that has the energy density and the reliability and all of that to tackle it. Yeah. For example, a 12-foot uranium rod can last 6 years in a nuclear power plant. Now, nuclear is non-renewable as well, but because the fuel lasts so long, we could theoretically be using nuclear for an extremely long time. In 1,000 years, I would hope that we've invented some sort of new technology like hydrogen fusion or something where we just don't have to rely on any of these. These will all seem primitive by comparison. Here's the relative energy densities of a bunch of different things. Lithium-ion battery is very low. That's why Teslas and electric cars are so heavy, because the fuel or the energy density of batteries is so much lower than gasoline. So you have to cram a huge mass of material into your car. And here's sort of the global picture of nuclear. And again, it really hasn't gone that far in the last several decades. If we look at the United States, well, I guess it's North America in purple, these bars really haven't grown much larger since Chernobyl. So it's sort of a scare thing. Here's a picture of it that really got everybody... It left a bad taste in everybody's mouths, which is really unfair because this nuclear accident was the worst one ever, but it was really mild. Yeah, about 35 people died, but that's nothing compared to in other industries. And the uranium in a plant can't explode. The Chernobyl plant, it was a steam explosion. It got too hot and the steam blew up and it spread the radioactive material all over the place. But the uranium and thorium in a plant like this can't blow up. So it's not like it's a nuclear bomb waiting to go off. Today it's covered by a sarcophagus that will contain the radioactive material. Here's a picture of, it's called the elephant's foot. That's like the uranium material that sort of got released, and it turned into molten radioactive metal because it was no longer contained and being cooled. Sorry, I went too far there. Yeah, so the danger of nuclear power is not actually a danger. Like, yeah, yes, bad things can happen, but they tend not to happen. Same kind of story with oil spills. They get a lot of press coverage and everything, but actually oil spills are at historic lows. They're not at all a problem like they used to be, and they won't be in the future. There's no reason really to think that they will be. The real drawback with nuclear is that it's really expensive, but if we start to innovate, then it can become cheaper. So that was a lot of information, but there we have the alternative forms of energy. Next time, we will talk about humans and our activity and our environmental impact.